this video, we're going to use what we've just learned about acid-base titrations and how they work to use titrations as a tool for determining the concentration of an unknown acid or base. The basic idea is this. We have seen that there's a dramatic shift in pH with very little change in volume right at the equivalence point. And so it's possible to pretty accurately catch what is the volume that's been added of the titrant right at the equivalence point. Well, if you know what's in the burette, if you know its concentration, and you can measure that volume, you can figure out the number of moles that have been added at the equivalence point. But at the equivalence point, you've just used up whatever was in the flask. So here's how titration is working to find an unknown concentration. First of all, at that equivalence point, the acid and base have reacted exactly. In other words, there's no limiting reactant. We also know the balanced chemical equation between the titrant and what's in the flask. And so stoichiometry can then be used to find the number of moles of the unknown, whether that's in the flask or the burette. And then molar concentration can be determined, if that's what you ultimately want, from moles divided by volume, as long as that volume is in liters. We're going to learn how to do this by looking at 3 example titrations. First of all, we have this titration. The question that we're being asked is, what is the concentration of the HCl? The HCl, if you look at this setup, is in the flask. We know we have 25 milliliters of it, but we don't know what its molarity is, and that's our objective. We have to find that. In the burette, our titrant is 0.200 molar NaOH. Here's the reaction between the two. NaOH from the burette will react with HCl, and that will produce water and NaCl. The stoichiometry is 1:1 between the acid and base, and that's going to be the really significant mole ratio in our calculation eventually. On the right-hand picture, we have the situation at the equivalence point. 24.62 milliliters of our base solution has been added. And if we're at the equivalence point, then that means the HCl has just been used up, but we haven't added any additional NaOH. So the number of moles of NaOH that we've added can be used in stoichiometry to figure out exactly how many moles of HCl were in the flask. Let's do it. Starting out with the volume delivered, we have 24.62 milliliters of our solution. And our solution is 0.2000 moles of NaOH per liter. Now, in previous calculations, I've used 1,000 milliliters instead of liter because I wanted the milliliters to cancel. But I'm going to show you a little trick here. I'm going to cancel out the liter part and just leave the milli there. So when I multiply these two together, I have millimoles of NaOH. And we're going to find out that for this calculation, that works okay. Now I need a mole ratio. I know from the balanced chemical equation that I just created that 1 mole of NaOH is going to react with 1 mole of HCl. So now I have millimoles of HCl. I'm going to stop my calculation right here, and here's my answer. 4.924 millimoles of HCl were in the flask. Now, what's the concentration? Well, the concentration of HCl is the number of moles divided by the liters. But it will also work to take millimoles, 4.924 millimoles, divided by milliliters. And there were 25 milliliters to 4 significant figures. When the milli part cancels out, I'm back to moles per liter, which is molarity. I have 4 significant figures in my answer. 0.1970 is the molarity. This concentration has a base in the flask and an acid in the burette. So we've got 30 milliliters of a KOH solution in the flask, but we don't know its molarity. In fact, that's the question. What is the concentration of the KOH? In the burette, we have 0.10 molar H2SO4, sulfuric acid. So what's the reaction? Well, if I'm reacting H2SO4, the acid, with KOH, a base, I'm going to get water and a salt, so H2O, plus K will be going together with SO4 to make our salt. Well, K is 1 plus, and SO4 is 2 minus, so the formula is K2SO4. To balance this, I'd have to have a 2 in front of KOH. That gives me 2 OHs. To go with the 2 H's from the H2SO4, I would have 2 HOHs, or 2 waters. So there's my balanced chemical equation. Looking at the equivalence point situation, 13.55 milliliters of H2SO4 have been added to our flask. And now, at the equivalence point, the KOH has just been used up, and I haven't added any additional H2SO4. So I can use stoichiometry to figure out how many moles of KOH were in the flask, and then I can get the volume involved to find molarity. So starting with the volume added from the burette, 13.56 milliliters were added, but the concentration was 0.10 moles of H2SO4 per liter. So just like in the last example problem, I'm canceling out the liters but leaving the milli. Mole ratio. Well, we've seen here from the balanced chemical equation that 1 mole of H2SO4 will neutralize 2 moles of KOH. So now I have millimoles of KOH, and I'm going to stop my calculation there. When I work this out to 2 significant figures, I have 2.7 millimoles of KOH. Now I need the concentration. Well, concentration of KOH is going to be the moles divided by the liters, or, like we saw in the last problem, millimoles divided by milliliters. So 2.7 millimoles of KOH must have been in that flask originally, based on the stoichiometric calculation that we just made. If I divide that by the volume of that flask, which was 30.00 milliliters, again, the milli cancels out and I get moles per liter, or molarity. I have 2 significant figures in my answer. 0.090 is the molarity. You try one. Here we've got a setup where we have NaOH, a base, in the flask, and we have HNO3 in the burette. It tells us that 32.44 milliliters have been added when you reach the equivalence point, and your job is to find out what is the concentration of the NaOH. Stop the video, give this a try on your own, and I'll bring you an answer in a little bit. Well, first of all, we want to establish what the balanced chemical equation is going to be. So I'll take NaOH, that's my base, and react it with the acid that's in the burette. NaOH plus HNO3 is going to give me water, H2O, or HOH, and a salt, and that salt is NaNO3. Well, this is balanced the way it's written, so the stoichiometry is 1:1. Now, just like we've done in the past, our starting point is going to be the volume that's delivered from the burette. So starting with 32.44 milliliters, I'm going to multiply by the molarity of the titrant to find out the moles of HNO3 added at the equivalence point. It was 0.115 moles of HNO3 per liter. So with liters canceled, I have millimoles of HNO3. But I want to know how many millimoles of KOH were in the flask. So I'm going to use my mole ratio of 1:1 from the balanced chemical equation. 1 mole HNO3 reacts with 1 mole of NaOH. So with moles of HNO3 canceled out, I now end up with millimoles of NaOH that were in the flask. The numerical answer here to 3 significant figures is 3.73 millimoles. So the concentration of the NaOH that was in the flask initially is equal to 3.73 millimoles divided by 15.00 milliliters. Again, the milli part cancels out and just leaves us with moles per liter, which is molarity, and the numerical answer is 0.249 molar. These calculations are not very hard. The only difficult thing is sometimes it's hard to visualize exactly where you should go with the calculation, but there's always going to be a neutralization reaction, an acid-base reaction in these titrations, and your starting point is almost always going to be volume added from the burette. Now, it's possible that you could be asked to predict what the volume is going to be at the equivalence point, but I think if you understand how titrations work and have done enough of these calculations in practice, you'll be able to figure that out in time.